Saritha Kumari, working as Assistant Professor, EEE Department at Institute of Aeronautical Engineering College. Today my topic is about long answer questions based on series parallel circuits and Kirchhoff's laws and ideal practical sources. So the question is it possible to connect directly two current sources 5 amps and 3 amps in series? And similarly, can we connect directly two voltage sources 2 volts and 6 volts in parallel? Justify your answer. So basically the question is talking about series connection. First part, you can see in the question, they're asking, is it possible to connect directly two current sources 5 amps and 3 amps in series? And next part of the question is talking about the parallel connection. Can we connect two voltage sources? They're talking about two voltage sources 2 volts and 6 volts in parallel. So they're asking, is it possible? And also justification. So basically to answer this question, we need to recollect the basic points of series circuit and parallel circuit. So in series circuit, we know that in series circuit, current flowing through each element is same, and but voltage divides. Voltage is going to divide across all the elements in the circuit. So that is a series circuit. So you can see in the answer, that is a point mentioned. A series circuit has only one current path. So that is the meaning. So basically we know, you can see in the picture, the small circuit, series circuit, where three resistors, resistor 1, resistor 2, resistor 3, these three elements are connected in series. Okay. So, and they connected to a voltage source. So here a series circuit, in series circuit, only one current flows in the circuit, so which is I, you can see. So only it has only one current path. So that is a point in series circuit. So here it is an example to a battery voltage source. Here two lamps are connected in series connection. So for the first part of the question, is it possible to connect directly two current sources? They're asking two current sources 5 amps and 3 amps in series. Is it possible? But we know that in series circuit only one current flows. So the answer is it's not possible. So for the first part of the question, the answer is it's not possible to connect two current sources in series. Different current sources, okay, which are given different magnitudes 5 amps and 3 amps. Okay, it's not possible. Next, coming to the second part of the question, similarly, can we connect directly to voltage sources 2 volts and 6 volts in parallel? Two different voltage sources, okay, magnitudes are different. So is it possible to connect them in parallel? So you have to recollect the parallel circuit basic point. We know that in parallel circuit, there is only one voltage across all the parallel connected elements. Okay, but current divides. The supply current or total current in the circuit, that is going to divide across all the parallelly connected elements. So based on that point, so here see that is mentioned, a parallel circuit has more than one current path branching from the energy source. Okay, that is what the meaning. The total current is going to divide across all the parallelly connected elements. That is the meaning. So here you can see there are resistors, 4 resistors, R1, R2, R3, R4, which are connected parallelly, which are placed parallelly to a supply, across a supply voltage Vs. Okay, so from this supply voltage, the current is coming, let us say I or Is. Because supply voltage is Vs, say that supply current is Is. So which is going to divide across all the resistors which are connected here. So which is going to divide as I1, I2, I3, I4. Okay. So that's why that is a parallel circuit. Okay. So current is going to divide Okay, and here, but the voltage across each element is same. What is that voltage? Across R1, the voltage across the R2, voltage across R3, across R4, across all the elements, the voltage is Vs only. Okay, so that is a point. So voltage, as you can see, also it is mentioned the voltage across each pathway is the same. Okay, so come back to the question asked, uh, can we connect directly two voltage sources, 2 volts and 6 volts in parallel? So different voltages they're telling about. So it's not possible to connect two different voltages in parallel, because in parallel the voltage across each element is same. Okay, so that is a justification. Okay, next question. State and explain Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law with suitable examples. Okay. Question is state and explain Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law. Okay, with suitable examples. Okay. So first we have to explain about the each about each law, and then we have to give the example also. Okay. So first is about the Ohm's law. So Ohm's law, it states that at constant temperature, potential difference V across the ends of a conductor is directly proportional to the current I flowing through the conductor, right? V proportional to I. Okay, so that is Ohm's law. At constant temperature, the potential difference V applied across the ends of conductor is directly proportional to the current I flowing through the conductor. Okay, V, that is nothing but mathematically V proportional to I. So here, um, what is a proportionality constant? Here, that is the same expression. It is shown here. V is equal to proportionality constant is R. Okay, here proportionality constant is R. So V is equal to R into I. R into I. So that is a proportionality constant. Okay, which is called resistance. Which is called resistance of the conductor, which can also be written as R is equal to V by I. Okay, V by I. So that is just a I'm giving a brief explanation about Ohm's law, because already clearly I explained in my previous lectures. Okay, about Ohm's law clearly, very clearly. So once again I'm briefing here. Now example means just to take some value of voltage 10 volts and current flowing through the, when supply voltage V is 10 volts is applied, current flowing through the element is 5 amps, let us say. Then what is R? What is the resistance of the conductor? So you can mention like that and calculate. R is equal to, from Ohm's law, V by I. So 10 by 5. That is how we can give the example. Next, Kirchhoff's current law. Kirchhoff's current law, what it says. So we know that Kirchhoff's current law talks about the currents, which states that the algebraic sum of all the currents entering and leaving at a junction or node is 0. Okay, algebraic sum of currents, all currents entering and entering and leaving at a particular point. What is that point? In the circuit, it may be junction or a node. Okay, is 0. So the same statement can also be mentioned like this. Okay, before that, this is a mathematical expression. Sigma I is equal to 0. Sigma I is equal to 0. Now the statement can also be mentioned like this. Sum of currents sum of currents flowing towards a junction is equal to the sum of all the currents flowing away from the junction. Sum of entering currents equal to sum of the leaving currents. Okay, the statement can also be mentioned like that. Okay, now we can give an example for the KCL. Okay, so we have example for the KCL in my previous lecture. Okay, so take a small circuit with showing some incoming currents at a particular junction or node, and also leaving currents, and apply KCL at that particular junction and find some unknown value. Okay, so that is how you can show the example. Next one is Kirchhoff's voltage law. So what it says about, so we know in the name itself it is there. Kirchhoff's voltage law talks about the voltages. So it states that algebraic sum of all the voltages around a closed path, okay, is zero. In a simple way, that is a statement. Algebraic sum of all the voltages, okay, in a around a loop, around a closed path is zero. Now here mathematically, which is given as sigma v equal to 0, and sign convention for this to apply the KVL. So if there is a sign convention, okay, previously there is a sign convention for KCL also. Okay, so here actually all entering currents taken with positive sign and all leaving currents taken with negative sign. Okay, so while applying KCL. Okay, now KVL sign convention. So the sign for battery voltage or battery EMF. Okay, so if a rise in voltage, okay, if we are moving from negative terminal of the battery to positive terminal, that means voltage rise, lower potential point to higher potential point means a rise in voltage, which is taken with positive sign, and fall in voltage for a battery means we are, if we move from positive terminal of the battery to uh, uh, negative terminal of the battery, higher potential point to lower potential point, that is fall in voltage, it is taken with negative sign. Okay, while applying KVL in a loop, in a closed path, okay, that is how the sign convention. Next, for sign convention for IR drop, voltage drop. IR means voltage drop. Okay, so the sign convention for this is when the direction of the assumed current is same as the direction of the IR drop. Okay, if the direction of the assumed current is same as IR drop, then that is taken with negative sign. Okay, then that IR drop is taken with negative sign. Okay, and vice versa. Okay, so clearly you can see here in the picture. Okay, this is already I explained clearly in my previous lectures. Okay, about the sign convention. Okay, in KVL also. Okay, so example. How do so for KVL example? So take a small circuit with all voltages given. Okay, so this is also explained in the previous lecture. So a small circuit KVL example I'm talking about. So battery, let us say 10, then so this is given 1 volt, let us say, and this is not given, and this is given 2 volts. So find out this VR2, right? Supply voltage is given and voltage drops given, only one voltage drop is unknown. So while applying this KVL in this loop, we can calculate that unknown value. So next question is about the make short notes on practical sources and ideal sources. Okay, that is the question. Short notes on practical sources and ideal sources. So you need to know what is meant by ideal source, what is meant by practical source. So we know that already. Ideal source means that may be a voltage source or current source, okay, which are imaginary electrical sources which maintains or which provides constant voltage or constant current, which provides constant voltage or current to the circuit regardless of the load, regardless of the load connected. Okay, these that means whatever may be the value of load, so it provides constant voltage, constant current to the circuit. And these ideal sources do not have any internal resistance. That is a main point. Okay, ideal sources do not have any internal resistance. And uh, here we need to know it is impossible to build a source with zero internal resistance. Okay, so practically speaking, it is impossible to build a source with zero internal resistance. So all the sources are, all the real sources are, okay, existing sources are practical sources only. Okay, that is a final point. Okay, coming to the characteristics. Okay, so here you can see here on the in the picture, so there is a voltage source. Okay, first one is about the voltage source. It is talking about, okay, how is ideal voltage source, you can see. So here a voltage source, this is a symbol, right? So voltage source across AB terminals, okay, its voltage is simply V only. Okay, and if we draw the characteristics taking the voltage on y-axis and the load, okay, current means here on x-axis current means load current on x-axis. Even though we go on increase the load, okay, we move on increasing the load, or if we move on no, I mean as the time varies, okay, okay, the voltage maintains constant, the voltage source maintains its value, its magnitude constant value. That is the ideal voltage source. Next, beside one figure B, you can see a practical voltage source. Okay, that means previous one is ideal. Okay, so this figure B shows the practical voltage source. So practical voltage source means just now we have seen in the above point that it is impossible to build a source without internal resistance. Okay, zero internal. So always we have the real source of practical. So voltage source is provided with the internal resistance. Okay, what is that? It is connected in series. Okay, that is a basic point. Already this is explained also in the previous lecture. Okay, so once again I am briefing here. So a voltage source has its internal resistance in series, okay, in series with the source, so which is shown here. Its resistance is denoted with R. So where so there is a resistance means definitely current also flows in the circuit, okay, depending upon this resistance value. So if we draw the characteristics, if we draw its characteristics taking the voltage on y-axis, okay, and current, load current on x-axis. So what happens here, if we go on increase the current, load current, automatically this current magnitude increases means the voltage drop appears across this resistor also go on increasing. Okay, if we go on increase this current, load current, what happens, automatically the IR drop. Okay, here the voltage drop across this resistor. Okay, current increasing means voltage drop also increasing. So parallelly the voltage source, the supply value decreases in its magnitude. So that is what you can see, practical source. Okay, because of the increase in voltage drop, if we move on, the voltage also okay, it slowly falls down. So that is a practical voltage source. Okay. Next is about the current source. So you can see down the ideal current source, which is figure C. So a current source, this is a symbol with an arrow in a small circle. So across the terminals AB, what is the current? So it is same as supply, so supply current, okay, I only. So if you draw the characteristics by taking this current down y-axis, okay, and voltage or time, okay, if we move on with respect to time, move forward with the time, okay, so what happens, irrespective of the time increasing our voltage, what is the current, ideal current source, which maintains its value constant, right? So that is a ideal current source, okay. Even though if we move on increasing with respect to time, go forward with respect to time, its current, the current source maintains its value constant, okay. Now next figure, beside that, you can see, we can see practical current source, practical current source, okay. So here the practical current source means definitely there will be a resistance comes into the picture. So know that the current source has its resistance, internal resistance, always in parallel with it. So that is what you can see here. So now coming to the characteristics. So because of this resistance here, so what happens if we move on, if we move forward with respect to time, or if we go on increase, okay, increase or move forward, what happens is the voltage drop, okay, the voltage drop across this resistor also increasing, okay. That means the current drawn by the this resistor, internal resistance, also increasing, okay, because if we are moving forward, okay. So automatically current, this supply current reduces its value from its initial value, okay. So that depends on the, that depends on this resistance value, okay, because if we are increasing this value, automatically current drawn by it also increases, automatically the supply current also, okay, slowly move, go on decreasing. Next question is, estimate the equivalent capacitance of series and parallel connections of capacitor elements, okay. Next question, estimate the equivalent capacitance of series and parallel connection of capacitor elements. So when capacitors are, number of capacitors are in series connection, what is its equivalent value? And next, parallel, when number of capacitors are connected in parallel, what is its equivalent value? So this is also explained, okay, in my regular previous lectures. So once again I'm briefing. So here first consider when capacitance is in series. When capacitance is in series, okay, what is its equivalent value? Considered here two capacitors C1, C2, two capacitances are, okay, connected in series. So C1, C2. So and they are connected to a supply voltage V. So what happens? We know that. So that is what they mentioned here. Two capacitors to a set to mix series means what? Same current flows through all the capacitances. Okay. So basically that is the point. So series connection. Now, so let us say that current is, okay, I. Now in parallel connection, we know that current flowing through all the elements is same, but voltage is going to, supply voltage is going to divide, okay. So let us say because two capacitances, the voltages are V1, V2, okay. So now that is what mentioned here. Applying KVL to the loop, total voltage is equal to the sum of all the voltages in the circuit, V1 plus V2. Okay. Now we need to consider the voltage current relation in case of a capacitor. Okay, voltage current relationship in case of capacitor. So what is that voltage current relationship in case of capacitor? V is equal to, it is like Ohm's law only, right? So V is equal to 1 by C integral of I dt. Yes or no? So in case of resistor, that is given by V is equal to R into I. Okay, in case of inductor, V is equal to L dA by dt. Okay, and in case of capacitor, V is equal to 1 by C integral of I dt. So we need to, these are the very basics, always need to remember. So consider that V is equal to 1 by C integral of I dt. So here write down what is V1, what is V2. So V1 is given by 1 by C1 integral of I dt, because current in the circuit is same, and V2 is given by 1 by C2 integral of I dt, right? And V is given by 1 by C equivalent, total equivalent, okay? Or total C or equivalent C. So 1 by C equivalent, integral of I dt. So that is how we substituted. So cancel the similar terms on both sides, that is integral of I dt. So this is given by 1 by C equivalent. 1 by C equivalent is equal to 1 by C1 plus 1 by C2, right? So that is a equivalent capacitance when capacitors are two capacitors here. So two capacitors connected in series. Okay, next similarly, derivation, equivalent capacitance when capacitance is connected in parallel. So we basically, always the basic point in parallel connection, the current supply current is going to divide, but the voltage across each element is same. So here, that is what mentioned, two or more capacitor but the same if same voltage appears across each element. So now two capacitors C1 C2 are in parallel here. So and the source is taken current source, okay, so which is going to divided as I1 and I2. Okay, let us say the voltage coming from the voltage with respect to this supply current is V. So voltage across each capacitor is V only. So now, so here in the parallel circuit, supply current is equal to the sum of all currents, right? So that means supplying KCL, we write it as I is equal to I1 plus I2. Now once again recollect the voltage current relation. In case of capacitor, we know that 1 V is equal to 1 by C integral of I dt. Okay, that is a basic relation. So from this, what is a current value we can get? What is a current? Okay, what is a current expression in terms of voltage and capacitor? I is equal to C dV by dt. Yes or no? Right? So we see integral of I dt, but we want only I. So we need to remove this integral. To remove that integral, differentiate on both sides. Differentiate on both sides. C, okay, that is a constant. So dV by dt, and for current this integral goes, it becomes I. So that is what it is mentioned here. I is equal to C dV by dt. Now write down what is I1, what is I2, right? I1 is given by C1 dV by dt, right? I2 is given by, voltage is same, right? In parallel circuit, voltage across each element is same, right? So that's why I1 is C1 dV by dt and I2 is C2 dV by dt. Okay, now on the other side, what is supply current? Total current in the circuit in terms of C and voltage. C equivalent, Okay, total capacitance of the circuit, okay, multiplied with dV by dt. So cancel the similar term on both sides. So the finally the equation is C equivalent is equal to C1 plus C2. So that is the expression when capacitance is in parallel. When capacitance is in parallel. Okay, that's all for now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.